Hello, and welcome to Astronomy 100. In this segment, we're going to wrap up the topic of stellar properties, and we're going to focus our attention on determining the distances to the stars. To many people, this sounds like a kind of a trivial topic. You are very familiar with judging distances and measuring distances in your daily life, especially in our modern world with Google and mapping and all sorts of GPS units that will tell us distances very easily and very precisely. Turns out, though, in astronomy, it's very difficult to determine the distances to the stars. Primarily, the reason why is because when you look at the stars, they can have different amounts of energy that they produce, and that amount of energy can fool you into thinking a star is close, in reality it's far, or vice versa. So what we're going to do is talk about how it is that we get around this problem. But let me first show you a couple of things that you do on a daily basis that you may not even realize that you're doing when it comes to judging distances. So in this first picture here, what I want you to notice is this is just a picture of a typical parking lot. We have certain things that we do without thinking twice. For instance, you know when you look at this picture that even though these cars look larger and these cars way off over here look smaller, you know in reality that cars are generally the same size. And so you can actually judge the distance to a car in this parking lot by how big it looks. The cars that look big are close, the cars that look small are really far away. We do this without even thinking about it. Another trick that we do is that we can judge the distance to mountaintops or hilltops by the amount of haze that you see in the atmosphere. Notice that these hills that are, well, of course, close to us, these hills don't seem to be quite as hazy. They're a little more clear, a little sharper in focus. And then as you get steadily further and further away, the amount of haze increases, the particulate matter in the atmosphere increases, and you can tell that a very distant mountaintop is distant because of the clarity of the image. That's one way that we also judge distances. But let me show you how sometimes these things don't work so well. For instance, the Apollo astronauts, when they went to the moon, one of the things that they struggled with was judging distances. The reason why is because there is no air on the moon, and with no atmosphere on the moon, there is no haze. And so you can look at a very, very distant mountaintop and look at one that might be distant or it might be close. Notice the clarity of each of these is the same. So it may look like they are at some particular distance that you can't be sure of because the normal trick that we use to judge distances is just not available. So the other thing, of course, is that when you look at a very far away boulder, is it a boulder that's small or a really large boulder? The clarity, of course, is not going to be the same for either one. If it were an automobile, you could judge, obviously, the distance because you know how big an automobile should be. So we tend to do things like that to help us judge distances. Let's switch to the stars. One of the things that you do without even really thinking about it is you often judge distances of light sources by how bright they are. When you look at a porch light or an automobile headlight, you might notice that the automobiles that are far off in the distance coming towards you have very faint headlights, and then of course as they get closer they look brighter. So you can actually estimate the distance to an automobile just based on how bright the headlight looks. The problem though is that all headlights on automobiles are standard. So you can reliably assume that a faint looking headlight must be far, and one that looks bright must be close. If automobile headlights weren't standard, if some of them could produce lots of energy and some headlights produce just a little bit of energy, then you would never be safe in making that judgment, that assumption. So if we look at this picture here, you'll notice that these stars, we're using the constellation of Orion, but you notice that these stars have different brightnesses. The problem is, are they bright because they produce a lot of energy, or are they bright because they're close? And if you remember in a previous segment, we talked about the comparison of the concept of the apparent magnitude of a star as well as the absolute magnitude. So if you just look at the stars in the sky, and if you assume that stars that look bright are close and stars that look faint are far, you may or may not be correct. If I were to show this picture to just anybody walking down the street and say, hey, use your intuition, which one of these stars would you guess is the closest star? I'd be willing to bet that they would pick either this one or perhaps this one. They would probably never pick this one or this one, because what they're going to do is say, well, a star that looks bright must be close because it's bright. So the issue is we can't rely on that. We can't assume that. So how do we determine the distance to a star without using its brightness? The way that we do this is one final method that you use on a daily basis that you may not even realize that you're doing. It's a concept called parallax. So let me show you how this works. In this concept called parallax, what we're going to do is show you an animation here. And in this animation, you're in an imaginary room, and you're simply walking left and right. You're not going into the room, you're not coming out of it, you're just simply walking left and right. And notice the odd shapes in the room. But as you walk left and right, you'll notice that your perspective of these objects change. Now what I want you to notice is you are moving back and forth, but the shapes are not actually moving in reality, but they appear to move. You'll notice that the shapes that are very far away are moving not so much, just a little bit. And the shapes that are closer to us are moving a lot. So what you do is you can actually judge the distance to an object based on how much it appears to be moving relative to how you're moving. You do this in a car all the time. The stuff along the side of the road whizzes by so quickly you can't even tell what it is, but maybe a house way off in the distance moves by slowly and you can study it and look at it how it looks, assuming you're the passenger, of course. So parallax is one way to judge distance based on the appearance of movement. Now, how does this translate to astronomy? In this example here, what I want you to notice is that we have the Earth orbiting around the sun, and this is the top-down look. So you're looking down on the top of the sun, and this is the orbit of the Earth. Let's imagine there's a star nearby, and what we're going to do is change it from being close to far back to close again. So what I want you to notice is as we move around the sun, the star is not doing anything at all, but our movement creates the illusion that the star is shifting back and forth. So this appearance of a shift is caused by us doing the movement. But notice when the star is far away, the shifting is very slight or smaller. And when the star is much closer, notice that the shifting is much larger. So what you can say is there's a correlation there. And the correlation is a star that is far away has a small shift, and a star that is close has a large shift based on our movement. So remember, we're the ones doing the moving, but the illusion is that the star is shifting back and forth because of where it is. This method is called trigonometric parallax, and the reason why it's called that is because what develops in this situation is a triangle, and the mathematics of triangles and other shapes is called trigonometry. So this is called trigonometric parallax. Now let me show you how this can be put into actual practice. The first thing I want to show you is kind of a cool video here, or animation I should say. Let's define trigonometric parallax. It's the apparent shift of a nearby object with respect to a distant background due to the fact that the observer is doing the movement, right? So remember, we're the ones moving, and an object looks like it's shifting because of its distance. Now, in this animation, it's very, very subtle, but here's what I want you to notice. Do you notice how all the stars seem to be kind of moving back and forth collectively to the left and to the right? What this is a recreation of how the stars that are near the constellation of Orion would appear to shift because of somebody orbiting around the sun. Now, it's not any particular planet. This was made for an imaginary planet that has an orbit that's much bigger than Pluto's orbit, so way, way out there. And if you're way out beyond Pluto, you make a big, big shift back and forth. You know, your orbit is big. You're going from one side of the sun to the other side of the sun. Now, notice how the stars are shifting back and forth. But notice how they're not all the same size shift. Do you remember that we said that most people would have picked this bright star or this bright star to be very close? Notice how these two stars seem to be shifting the least. So remember, what that means is small shift equals big distance. So these stars turn out to be really very far away. And if you would assume that the bright ones are close in this case, you would have been wrong. Now look over here. you'll notice that some of these stars are shifting quite dramatically. Remember the rule, large shift means closer to us. So in reality, the closest stars to us in this field of view ended up being very faint. And so your assumption of bright equal close is really just not a good one at all. So we can turn the size of the shift into a measurable distance. So how do we turn the concept of trigonometric parallax, this appearance of shifting because of our movement, how do we turn that into an actual number? How do we quantify that? Let me show you how that works. The way that we quantify it is we build a triangle. So let's start with this example. Let's say that we want to know the distance to this planet, and we have an observer on this side of the Earth with their telescope, an observer on this side of the Earth with their telescope. Here is the view from the person standing here, and here's the planet. Here's the view of this person standing here, and here's the planet, same planet. Notice that from this perspective, the planet appears here. From this perspective, the planet appears here. So notice the planet is in two different places based on where you are. Well, notice the triangle. So what we end up getting is the appearance of this planet shifting back and forth against the background stars, and it's all dependent upon our distance. So what I'm going to do is put in some variables, and I'm going to bring up a formula for you. What we're really interested in is this distance here, the distance between the Earth and this planet. We're going to call that d. The shift is what we're going to call the parallactic angle, and we're going to call it the letter p. So notice over here is the formula, and notice the p is down below. So this is an inverse relationship. When the value of p becomes large, then the value of d becomes small. Remember, stars that shift a lot, or when an object makes a large shift, that means they're close. So lots of shifting, big P, makes a close distance, or small d. So we can actually measure the size of P and determine the value for d. Let's apply this to the stars. So now we have gone so that we are showing the orbit of the Earth around the Sun. And what you'll notice is the Earth is on this side of the Sun, and then the Earth moves to this side of the Sun in January, and then over here in July. We get the same triangle though. So here's the nearby star, and watch what happens if we have a star that's close versus a star that's far. What you'll notice is the triangle changes. And what you'll notice up top is the amount of the shift becomes more or less depending upon the distance. So all we need to do is ride the Earth and photograph this star, and as we ride the Earth to the other position, photograph the star, and we can compare the position of the star against the background. Let me kind of do a mock-up of that. Let's say we take a picture of the star, here it is, in January. Here's the background. And then if we take another photograph of the same field of view in July, notice that the position of that star is in a different spot. What we then do is we measure the size of the entire shift, and then we want actually half of that. The triangle is actually half of the total shift, and once we get that value there, we just simply plug it into the formula and we measure the distance. So trigonometric parallax allows us to measure a noticeable shift and then use that size of the shift to tell us the distance to the stars. Now, one final thing that goes with this though, here's the problem. Remember, when a star becomes further and further away, the amount of the shift becomes less and less and less. There is a point where the star is so far away that we don't have a measurable shift anymore. So in reality, there's a limit to how far away a star can be for this method to work. And based on modern technology, that limit is about 1,600 light years. So if a star is further away than 1,600 light years, then its shift is too small for us to measure. Now let me put this into perspective for you. What that means is there's this bubble that surrounds the sun that we can measure the distance to stars using the method of parallax. 1,600 light years sounds like a lot, but let me show you how in reality that's not very much. If this is the Milky Way galaxy, here is the location of our sun. And if we can measure the distances to stars that are 1,600 light years away or less, the problem is that we can only measure distances out to the size of this dot. So anything inside of this yellow dot, we can measure the distance using parallax. If it's outside of that distance from our location, parallax won't work. The stars just will not have a measurable shift. So in reality, trigonometric parallax works very, very well as long as the stars are close enough for it to work. But if we're measuring the distance to an object that's too far away for a measurable shift, we have to rely on a different method. And what we'll do in the next segment is I'll show you that different method that we can use. I hope you'll join me.